Howdy students, welcome to Psych 3 Lab, Module 7, Time Series and the Analysis of Longitudinal Data, or in other words, what we're going to be learning is how to do some ARIMA modeling. So some objectives for today, I'm going to give an explanation of ARIMA models, and we're going to talk about seasonality and stationarity in ARIMA models, which is the I in that ARIMA. We're going to talk about differencing. I'm going to give you an explanation of the AR and the MA terms in ARIMA modeling, and then talk about our classic coding tutorial. So, just to start, ARIMA stands for Autoregressive Integrated Moving Average, which I know is a mouthful, but you can separate this into three different parts. You can start off with the autoregressive, also known as your P, which refers to the lag function of the difference series. An autoregressive model makes use of a previous time step to make a prediction about a future time step. That's essentially what that autoregressive, it's regressing onto itself. The integrated portion, otherwise known as the D, is the number of differences used to make a time series stationary. And we'll be explaining what it means to have a stationary data set a little bit later. And then additionally, moving average, also known as your Q, which is how much the average changes from one time point to the next. So in short, an ARIMA model uses previous time periods to predict outcomes in the future. So it's using what it knows to predict and forecast into the future. So our goal for today we're going to be running a series of statistics that fit the best fit ARIMA model given our data. By fitting this model, we'll be able to forecast what the data in the future will look like. So we're using time series data to forecast into the future. We'll be calculating three components. It's going to be the AR, the I, and the MA. The AR is the number of lags needed in the stationary series, so it assumes that your data is stationary. The I is the number of differences needed to make the data stationary, or the number of non-seasonal differences. And then lastly, the MA is the number of lags of the forecast error, the number of moving average terms. So we're going to be adding in these terms. With these components, we're able to fit a model that can properly forecast future events. So there's three components I wanted to talk about. There's a seasonal component, which refers to fluctuation of the data related to calendar cycles. Usually seasonality is fixed at some number. For instance, it could be like a quarter, a month, or a year. So something every month or every year, it changes its seasonal components to it. The trend component is the overall pattern of the series, and then the cycle component consists of decreasing and increasing patterns that are not seasonal. Usually trend and cycle components are grouped together, but the trend cycle component is estimated using moving averages. So let's talk about this idea of stationarity. A stationary model is one that does not have seasonal component to it. In other words, the day/month/year or even the decade does not influence what the data point will be. So we can see on the top here what an example of a stationary data set looks like, where essentially it doesn't matter where you choose on this, it's going to be completely random, the point. Whereas on non-stationary time series seen here on the bottom, you can see that, if I choose something in the later series, the outcome is going to be much lower than if I chose something at the very beginning. So that's what a non-stationary time series looks like. So ARIMA models have these two assumptions. One, your data should be stationary. And by stationary, again, it means that the properties of the series doesn't depend on what time it was captured. And additionally, there's no seasonality in the trend. Additionally, another assumption is that data should be univariate. In ARIMA models, only work on a single variable, so a single outcome variable. But this idea of data should not be stationary, what I want you to do is go ahead and look at these graphs on the left here and tell me which graphs seem stationary to you. I'll give you a little bit of time. You can pause the video here. So if you pause the video, you hopefully came up with the answers of at least B. G was a little bit of a tricky one, but B and G are both stationary data sets, in which point it's saying it doesn't really matter when you choose it. Even though there's a spike in here, overall it's kind of random as to what it's chosen as here. And then same with G. Even though G might look like it's got some cycles to it, those cycles just happen to be aperiodic. And I kind of know that from reading up on the research on it. But essentially B and G are both stationary data sets. So how do we make a data set stationary? If we have this assumption that data is stationary, we use something called differencing, in which differencing is computing the difference between consecutive observations. The more seasonality our data has, the more differencing that we're going to need to do. The nice thing is we're not going to be doing this by hand. We're going to be having the R packages do all this for us. The T-series and forecast packages in specific are going to be doing the differencing for us. So by determining the number of differences you need, you have figured out the I in your ARIMA model. This is otherwise characterized as a D. So it's either an I or a D. So what about the AR and the MA portions of the ARIMA model, right? What exactly does this mean? So we'll be looking at displays later, and the slides determine what the best AR, otherwise known as P, and the MA, otherwise known as Q, terms for our model will be. But in the end, we're going to get these models that look like this. So ARIMA P equals 1, D equals 1, and Q equals 1. In short, what we're saying is that models require one autoregressive term, so the AR, one differencing term, and one moving average term to help fit the best model. A model with an AR term in it specifies that the model tends to return to its mean relatively quickly. If it had an AR term, then it would indicate that there's an oscillatory pattern associated with it. A model with an MA term shows that the moving average tends to experience these shocks, as in the severe spikes in the data. The more MA terms we have, the more shocks the model has. So a couple of notes before we get started on the R tutorial here. The process of fitting an ARIMA model is completely exploratory. So in other words, we'll be using statistical tests to guide our decisions, but different people may come to different conclusions on the ARIMA model. So it's okay to come to a different conclusion on the ARIMA model. It's all about forecasting, and no one's really quite sure what the best forecast is going to be. Some component of this, and then additionally, some components of this unit are going to seem like a black box. The program's going to be doing a lot of the work for us. The underlying equations and processes are really beyond the scope of this class. I don't really have a full handle on to what all the equations are, but we're going to be doing it and letting R just kind of do some of the decisions for us. So let's go ahead and get started in R. So I'll go ahead and go open up my R Studio. Go ahead and create a new project. New directory, new project. We're going to name this module _07. I'm going to create that project. I'm going to go ahead and zoom in here for you guys. All right, and then we're going to go ahead and download the day.csv file from our module 7 lab. Module 7 lab, so it's the day.csv. Go ahead and download that data. Okay, so this has a lot of variables. We're not going to be using all the variables in this data set. Oh, yep, we want a CSV. I'm going to go ahead and do desktop, Statistically, module 7. Save it in. There we go. Okay, so let's go ahead and create in our notebook. I'm going to go ahead and minimize this. Go ahead and remove all the unnecessary tests, and then we'll go ahead and name this ARIMA modeling. And let's go ahead and create our table of contents. Okay, we can go ahead and save. And name this module 7 notebook. Okay, so let's go ahead and get started here. Okay, so before we get started, I want to just have a data set explanation. So this data set contains the daily counts of rental bikes between 2011 and 2012 in the capital bike share system with the corresponding weather and seasonal information. So this has a lot of variables in it, but the ones that I think of most interest are the date variable, which comes in as the date, season variable, which indicates what season the bikes are rented at, and the count, which is the number of bikes rented on that day. So what we're seeing is how many bikes rented on each day of the year. Okay, and we'll kind of look through it. We'll make a graph and it'll look a lot nicer as well. So we're going to be installing 2 new packages today. It's going to be the forecast package and the T-series package, and we're going to be using that for our ARIMA modeling. So let's go ahead and get started here. So let's go ahead and do hashtag load libraries. Insert a new R chunk. So we're going to do install packages. It's going to be quote forecast install packages. It's going to be quote T-series. We're going to be using library tidyverse library psych, library forecast, and library e-series. Okay, so let's go ahead and run that. And while we do that, I'm going to be loading up some notes here. There we go. Okay, so good. Got my notes loaded up in time here. Okay, so I'm going to go and hashtag out these two install.packages. I'm just going to play this again so we get some more time, or sorry, some more room. All right, so let's see what we have next on our slideshow. So we downloaded all the packages that we need. So we're going to be doing read CSV, but we're going to do something a little bit differently. If you use read.csv, please use read_CSV for this part of the lesson, but essentially we need to specify that the date variable is indeed a date variable. So additionally, we need to specify that it's a month, day, year format. It's telling it. So we're going to be doing something called call types in order to correctly call in the data set so that it reads in the date variable as an actual date as opposed to character string. Okay, it'll give you some problems if you don't do this. Okay, so we're going to go ahead and do hashtag import data. I'm going to do insert in our chunk. Okay, so let's go ahead and name this. We're going to name this daily underscore data. Use an assignment operator. We're going to use read_CSV. Don't use read.csv here. Do day.csv, comma, and then I'm going to go down a line and we're going to do call_types. Oops. Types equals calls, and we're saying find the whenever you see the date variable, once we're going to want to indicate that as a column date type variable. And the format of that is we use these indicators, which is percent lowercase m, which says it's a 2-digit month, slash percent lowercase d, which says it's a 2-digit year, slash percent capital Y, saying that it's a 4-digit year. Okay, and then we run that, and it's going to read in our variables, and we're manually saying that the date variable is going to be a date variable. And I can sort of show you what that looks like as well, just so we're all on the same page here. So let me just go ahead and open up that data set real quick. So this date variable, if we don't do this, it's going to read in as a character variable and it's going to give us problems later. So we're saying it's a 1 to 2 digit month slash 1 to 2 digit day slash 4-digit year. Okay, is what we're doing here. So don't save. So we go and run that. There we go. And it read it as a date variable, and then it converted it into a 4-digit year dash month dash day format for us. Okay, so go ahead and run that. Let's see what we got next on our slideshow. All right, we're going to go ahead and just select the variables of interest. So hashtag select variables of interest. Insert new R chunk. So we're going to name it daily. We're just going to rewrite over the daily data. Select daily data, comma. We're going to get the date variable, the season variable, and the C&T variable, which is our main outcome variable of interest. Go ahead and do that. Okay, so we have 731 observations of only 2 variables. I'm going to go ahead and bring this down so it stops doing that. And we see it's date, season, and count. Okay, go and look at our slideshow for the next thing to do. Then we're just going to go ahead and describe the data. So hashtag, go ahead and bring this up a little bit. Hashtag describe the data. Insert our chunk. So we'll do describe daily underscore data. Okay, So as you can see, it doesn't know how to read the date variable, so nothing's going to come up there. That's okay. That's totally fine. It gives us our seasons and then our count. So the average amount of bikes rented in a day was 4,504 bikes essentially. And it says that, oh, well, our median is kind of close to that. So that's pretty nice to see what we're going to do. So the next thing we're going to do, let me just check my PowerPoint to make sure, is we're going to go ahead and plot the data, right? So we want to see what the data looks like. So the way we do that is we are going to go, just bring this down a little bit. We're going to do hashtag visualize the time series data. So to do that, go to R. We're going to create an R chunk. We're going to do ggplot. And we're going to name our data set, which is daily data, comma, set our aesthetic, in which X equals date, comma, Y equals C and T, plus geom underscore line plus I'm going to set a ylab quote daily bike checkouts. Okay, and we go and run that, and there we go. So you might be looking at this saying, oh, okay, well, this definitely has some seasonality associated with it. So as you can see, as we get into the summer months, so this is around July and June here, we have more bikes rented, then it goes back down during the winter months, and then during the summer months it pops back up again saying, okay, people are more likely to rent these bikes during the summer. Additionally, it seems like more bikes were rented in 2012 than they were in 2011. So there's definitely seasonality to this, and this data is not stationary. But we're gonna be checking for that later from a statistics standpoint. So we're gonna do more than just eyeballing it. We're gonna be statistically asking, is this data stationary or not? But for now, it's not looking too stationary for us. So the next thing that we need to do, let me just see if this is correct. So yeah, I just wanted to go ahead and check to see, okay, is this data stationary or not? So we're going to be statistically checking for stationarity if this data is stationary. There's two steps involved in this. The first thing we're going to do is we're going to convert the data into a time series object using the TS function from the time series package. Then we're going to use a function called ADF.test function to test for stationarity. The ADF stands for Augmented Dickey-Fuller Test, and it assesses whether data is stationary or not. So let's go ahead and do step one. So let's go ahead and go back to our R. We're going to say hashtag check the stationarity of the data. We're going to do hashtag step one, convert it to a time series object. Okay, so let's go ahead and do a new R chunk. So the way to do that, we're going to name this as a new object. It's going to be called count TS, use an assignment operator. And then we're going to do TS, which is the time series function, and we're going to do daily data, and then you indicate what your outcome variable is, and our outcome variable is count, right? So the daily bike checkouts, that was that count variable, so we're converting that to a time series object. We go ahead and press play on that. Now we have a new object called count TS, which is a time series object. We can't click on it, we can't really view it, but it is there. Then do hashtag step two, check stationarity of the data. I'm going to do insert in our chunk. We're going to do ADF.test and then do count TS. So we put that newly created time series object in there, and we're going to do an ADF.test to see is the data stationary or not. Okay, so we ran that. What happened here is we got a Dickey-Fuller, we got a value, a coefficient associated with it. This lag order equals 9. These are both things that we don't necessarily need to concentrate on. And it's telling you that the alternative hypothesis means that it's stationary, which means if you have a p-value less than 0.05, then the data is stationary. Here, a non-significant p-value indicates that the data is not stationary. So we have a p-value of 0.7327, which indicates that our data is not stationary, right? And that's what we were looking at before. We were viewing this as well before. We're saying, yeah, this doesn't look very stationary to me. So we're testing statistically, is it stationary? And the question is saying, no, it's not stationary. The answer to our question is no, it is not stationary based on this augmented Dickey-Fuller test. So from here, we need to go ahead and turn our data into stationarity. So the first thing we're going to do is we're going to go ahead and transform our data. We're going to smooth our data first, smooth it by a monthly period. That's what this TS daily count frequency equals 30, because 30 is about the number of days in a month. We're going to smooth our data by 30, saying that smooth it by 30, so make it so that it's a much smoother graph and that you're assessing for the average of every 30 days. Then we're going to use something, the STL function, to go ahead and say, go ahead and look at this object and view it as a periodic object, okay? So first thing we're going to do is we're going to smooth our data. So do hashtag remove seasonality from our data. Okay. So let me just go ahead and do hashtag step 1, smooth the data. So we're going to do insert a new R chunk. So we're going to name this new object count MA, which stands for count moving average. We're going to use the time series function here. We're going to do daily data. We're going to get the count variable and then do frequency equals 30. Then we're going to do something called decomp, which stands for decompose it. We're going to decompose it. We use the STL function, which is essentially helping to smooth the data. We're going to do something called count MA, s.window equals quote periodic. This is part of this kind of black box that I was telling you about, where we're just letting R do it for us. So we go ahead and do that. So we have a new object called decomp, which is just a smooth version of our data essentially, and it's in a list form. Now let's go to the next step. Okay, yes, and it says set. I kind of give you some things. Sets up to smooth our data by month, and this is smoothing our data. Now we're going to go ahead and we're going to adjust the seasonality of it. So we're going to use a function called seasadjust and a difference function as well, which we're going to set that difference for the data as well. So let's go ahead and do hashtag step 2, difference the data. If I can spell. Okay, we're going to insert an R chunk. So we're going to name this D seasonal C&T. We're going to do an assignment operator, and we're going to use the C's adjust function on our decomp object. Then we're going to do count underscore D1, which is count with a difference of 1. So we're going to use the diff function. Then we're going to go D seasonal count, if I spelled that right. Count, I think I spelled that right. Comma, difference equals 1, or differences equals 1. I think that should work, and then we're going to go ahead and plot it as well. Plot count underscore D1. So this is the part where I'm going to say that the kind of black box comes in. What we're doing is we're seasonally adjusting it. Then we're taking our seasonal adjustment and giving it that difference of 1, so that I part of the model, and giving it a difference of 1. So we go ahead and play that. Oh, I think I spelled that wrong. Oh, I see what happened. There we go. E seasonal count. There we go. So we took a difference of 1. So remember from our slideshow before where we said that we're going to have to be taking a difference of 1. That's essentially what we did. So now this is what our data looks like with that differencing part adjusted for. So it doesn't look so seasonal anymore, right? It doesn't go up and then down during the summer months. Instead, we went and we adjusted the data so that we've met our assumption. Well, we're going to go ahead and check for it right now. We're going to run another ADF test to say, is this seasonal at all? So I go ahead and I give you the different, I kind of show you what each of these things are doing in the slideshow. And then we're going to go ahead and use the ADF.test again to confirm that the seasonality was removed. So let's do hashtag step 3, check seasonality again. We do insert in our chunk. We're going to do ADF.test. it's going to be the count underscore D1 variable. So we go ahead and play that. Okay, so now we're saying a p-value is less than 0.01 because the p-value is smaller than the printed p-value. It's less than 0.01. So we said that the data is now stationary. So we can work with this data in our ARIMA models. So that was a lot of steps just to get our data so that it was non-stationary, so that we met our assumptions. So remember, our two assumptions that the data is stationary and that it's a univariate analysis. And that's where we met that assumption with our new model now. So we have a destationized data, and we're working with only one variable. So the next step that we're going to do is we're going to start plotting our we're going to start figuring out what our AR and our MA terms are essentially. And to do that, we use two little graphs. We use an autocorrelation function plot and then a partial autocorrelation function plot to determine the AR and the MA portions of our model. There should be portions, not potions. So we use autocorrelations functions and partial autocorrelation functions to determine what to set our autoregressive and moving average aspects of our model to. So the ACF is used to determine what our AR should be, and the PACF is used to determine what our MA should be. So in the next set of slides, I'll be outputting an ACF and a PACF graphs. We'll literally be eyeballing the graphs to determine what we'll be setting our AR and our MA portions of our ARIMA model to. So it's really simple to create these graphs. So we're going to do hashtag get ACF and PACF plots to determine the AR and MA portions of our ARIMA model. So let's go ahead and insert a new archon. So the way that we create this ACF graph is it's literally a capital A, CF, and then count underscore D1, which is our deseasonalized data, essentially. We remember we tested it before, and it's deseasonalized, it's stationary data. We go ahead and run that. So the way that we look at this graph here is what we're doing is we're literally looking at this graph and saying, oh, and I'll show you, this plot shows the correlation of the series with itself with different lag functions applied to it. So this first line is with the lag function of 1 applied to it. The second one is with this lag function of 2 on it, and then 3 on it. What these are here are these are the 95% confidence interval bands. And what you're really doing is you're looking at these and saying, how many of these fall outside of the 95% confidence interval bands? Well, we have a few, right? But what we're mostly focused on is this one right here that has a huge spike in it, right? So to read this plot, we need to see how many of the lines fall outside the range of our 95% confidence intervals. So what we see right off the bat is that lines 1, 2, and 3 immediately fall outside of these confidence intervals. However, line 1 is the one that seems to have the most sharp decay after it. So therefore, we're going to initially set our AR, so the AR portion of our model, to 1. And the reason for this is because we want parsimony in our model. The less AR terms we set, the better. And we're going to see where this is all coming in a little bit later. But just know for now that because of this sharp decline from 1 to 2 of the lag terms, we're going to set it as a 1. Then we're going to go ahead and do a PACF chart. So the way that we do that, so I'll go ahead and do hashtag ACF plot, and then we're going to do a PACF plot. Hashtag PACF plot. And the way that we do that, we're going to go ahead and set an R chunk, and then it's capital P ACF, and then count D1. Go ahead and press play here. And again, we're running into the same thing here. So this plot shows the amount of autocorrelation at corresponding lags that is not explained by lower order correlations. And essentially, to read this plot, we need to see how many of the lines fall outside of the range of the 95% confidence intervals. So there's a few that fall outside the range of the 95% confidence intervals. But again, we're looking at this and trying to see which one has the sharpest decline so that we can encourage more parsimony with our model. So we see right off the bat that lines 1, 2, 3, 4, and 5 fall out of our confidence intervals. However, line 1 seems to be the one that with a significant and sharp decay after line 1. Therefore, we're going to initially set our moving average to 1 because we want parsimony in our model. The less MA terms we set, the better. And this is a part of the thing that I want to mention to you all. This is where people come to different conclusions about things by reading these plots, and they might come up with a different ARIMA model than us, but we're going to go with the parsimonious model for now. So let's go ahead and let's start modeling. So what we do is we're going to use the ARIMA function. I forget what package it's from, but we're going to use the ARIMA function on our D seasonal count. We use this the concatenate 1, 1, 1. This is saying our AR term is 1 that we determined is 1 when we looked at this plot here. And the difference is going to be 1 that we determined when we did the differencing of 1, and it made it so it was a significant, significant so that it's stationary. And then we set our Q to 1, which was set up because of our PACF plot that we looked at before. And then we're going to get a summary, and then we're going to get the confidence intervals of our model. So let's go ahead and do that. So let's go ahead, hashtag model the ARIMA model. It's a little bit different words, but we'll work with it for now. So the way that we do this is we're going to name this ARIMA1, our new object, ARIMA1. We're going to do ARIMA. We're going to use the D seasonal count data, comma, we're going to do concatenate 1, 1, 1. Again, we get that we're setting a moving average to 1, our P, our difference to 1, our D, and our autoregressive term is going to be set to 1, which is the P. Our differencing term is going to be set to 1, which is the D, and our moving average is going to be set to 1, which is that Q. Okay, so if we run that, we're going to get a new thing that's called ARIMA1. That's just a list of things. To output it, we do summary ARIMA1. We can go and play that. Okay, so we have an AR term and an MA term, and essentially what these terms mean is that the AR in the coefficient shows how quickly the time series model tends to pull towards the mean. The closer it is to 0, the more it tends to pull to the mean. It is significant because the confidence intervals do not contain 0. So let's go ahead and get those confidence intervals. So do conf int ARIMA1. So if we run all this again, we're also going to get confidence intervals associated with it. So we don't have significance values, but we can obtain confidence intervals. And we look at this for our AR1, and we say, does this contain a value of 0? And the answer is no. So we have a significant AR term. So we want to keep this within our model because we have a significant AR term. Then for our MA term, it's 0.887, which says an indication of the moving average behavior. So the closer it is to 0, the less the average moves. It is significant because the confidence intervals, again, do not contain 0. So we set up these confidence intervals again, and they don't contain 0. So we want to keep it in our model. Now, we're going to do some exploratory analysis. We're going to go ahead and do, sorry, I messed this up a little bit. We're going to be doing setting up our ARIMA models. So let's go ahead. And let's first do our ARIMA2 first, in which we're going to set an MA term. Okay, so we're going to do hashtag exploratory analysis. We're going to do insert in our chunk. We're going to do ARIMA2 to ARIMA, and for this, we're going to set our moving average to 2. So we're going to do D seasonal count, comma, C 1, 1, 2. So we're setting our moving average to 2. Summary, ARIMA 2, and then we're going to be doing conf int ARIMA 2. So we'll go ahead and run that again. So now we notice we have 2 moving average terms, which makes this model more complex. But we go ahead and we look again at our models. Okay, so our AR is still within the bounds. It doesn't contain 0. Same with our moving average one. It doesn't contain 0. However, our MA2 does contain 0. So that's what we're saying. Yeah, we probably shouldn't have this MA term model in here. It's not really explaining anything more in our model. So we're going to go and say we don't want to include the second MA term because the confidence interval contains 0. So the next thing we're going to do, ARIMA 3, in which we're going to set in a autoregressive term, another autoregressive term in there. So let's go ahead and let's do, what we can do is that we can actually go ahead and copy this. So we'll name this hashtag model1 to do model 2 to MA terms. And then we'll do hashtag model 3 to AR terms. So we're going to go ahead and set this so that we have 2 AR terms instead of 2 moving average terms. I'm going to run that. So now we have 2 AR terms in our model. And we can go and look, okay, so our AR1 still doesn't contain 0. However, AR2 does contain 0. So we're saying, yeah, no, that's probably not the best fit model there. And then we use the MA and say, okay, yeah, our MA still doesn't contain 0. Therefore, our best model is still our first model that we set up. Okay, our best model is still the first one that we ran, where we set everything to 1, because all the confidence intervals are outside the bounds of 1, and it's the most parsimonious model that we have. So we go ahead and we can say we're going to stick with our model 1. Then we can also use the auto.arima function so that it'll automatically pick the best model for us. So let's go ahead and use the auto.arima function. So do hashtag have our pick the best ARIMA model for us. We do insert in our chunk. We're going to name this new object called auto.arima, auto_arima, and we use the auto.arima function on our data, and then we're going to do dSeasonal count, comma, seasonal equals false. That's because we've already seasonalized our data. We don't need R to do that for us. So we're going to do summary auto_arima. And then we go ahead and run that. And as we can see, when we set the auto_arima, it came up with a model of 1, 1, 1 as well. So that's 1 autoregressive term, 1 differencing term, and 1 moving average term. So it came up with the same model that we came up with. It came to the exact same conclusions, thus making it so that we feel a little bit better about our model. Therefore, we can have more assurance that our model is the correct one. Then, to just sort of end this off, we're going to use an autoplot to go ahead and forecast our data. So let's go ahead and do hashtag visualize the forecast of the data. Go ahead and do insert our chunk. So we're going to be using some nested functions here. First, we're going to use autoplot. We're going to have it autoplot the best fit data. Then we're going to use forecast, comma, and then dSeasonal count. So we go ahead and run that, and we're going to get a cool looking graph. Oh, I spelled this wrong. There we go. Okay, and there we go. We got a cool looking graph here. So what's going on here? So just to take a step back from everything, okay? So what we've done is we set up a model that's going to forecast the seasonal count for us, forecast everything that's going to happen for us later. So remember, this is the number of bikes rented in a day, and we can see that it has this trend associated with it. Before we got rid of that trend so that we can go ahead and work with deseasonalized data, but we brought it back with this forecast function and the auto plot. And what we're saying is, okay, what is in the next coming months, how many bikes are going to be rented? So it's saying, you can see that it's looking up a little bit. This uses the monthly average to kind of make its forecast. So it's forecasting how many bikes that is expected to be rented in the next coming months. That's what the whole point of this is to be able to forecast from here. I know that the autoregressive terms and the moving average terms are a little bit complicated, but what we did is we essentially set up the best fit model to be able to forecast for the future in order to get this blue line, which is the forecast for the future. So that was a lot. This is really one of my first experiences with ARIMA models as well. But feel free to shoot me questions. I provide you some more references here as well and some resources so that you can go ahead and read up more on ARIMA models if you'd learn as well. I use them a lot. They really help me with creating this lesson. And what I'm going to be having you do is you're going to be trying to create your own ARIMA models in the assignment as well, in which case you're going to go ahead and follow along, try and do exactly what was done in the PowerPoint, and you're going to be working with some actual COVID data in the United States in which you're going to be trying to forecast what the COVID new cases rate is going to look like in the future. So I think it should be a pretty fun project. Go ahead and try it out. I think I gave some pretty detailed instructions. All right. Well, let me know if you have any questions. Thank you so much.